So where we left off was with the following theorem. If we had a set of vectors v1 up to vk that were mutually orthogonal non-zero vectors, and we had an element u that was in the span of that set, then the representation of u in terms of the v1 up to vk's were going to be just derived from the inner product. So basically our projections of u onto the direction of v1 and u2 on the direction of v2, and so on and so on. And so the question is now, if we're just given any old set of vectors, which are not necessarily mutually orthogonal, then what does the representation look like? For u being the sum of some beta sub j's times our vectors u sub j. So to begin to answer this question, let's just suppose that we are given a set of vectors, say u1, u2, all the way up to u sub k, and at least let's suppose that those vectors are linearly independent. Then what we want to do, or what we want to show that we can do, at least to simplify these things, is to take this set and turn them into a set of vectors, say w1, w2, all the way up to w sub k, such that the two spans are going to be equal. So our span of our u's is going to be equal to the span of our w's, and what we want is that the set w, our set of w's, so w1 up to w sub k, are not just mutually orthogonal, but are something called orthonormal vectors. And so we have a definition. So a set of vectors, say v1 up to v sub k, are orthonormal if and only if they are mutually orthogonal and unit vectors. That is to say that the length of each one of those vectors is going to be 1. And so these vectors kind of have the property that if we do the inner product with any two of them, so the inner product of vi and v sub j, that we get something that looks like 1 if I is equal to j, and 0 if I is not equal to j. So then this process of starting with a set of vectors u1 up to u sub k, and then we turn those vectors into an orthonormal set of vectors w1 up to w sub k. The process of taking those vectors such that the spans then still match, so our spans of u1 up to our spans of uk are equal to our span of w1 up to w sub k, is really taking this set of linearly independent vectors and turning them into what's called an orthonormal basis of these things. The procedure that we use to do that is something called the Gram-Schmidt Orthogonalization procedure. So let's take a look at how this is supposed to go. So in the Gram-Schmidt procedure, we're given a set of vectors u1 up to uk that are linearly independent. Now we'll kind of do this as a two-step process. So the first step is really to define a intermediate vector, a set of vectors v. In our first step, we'll just say, well, we're going to make v1 equal to u1. And then from this intermediate set of vectors, we actually turn into the vector that we want, w1, by normalizing or turning v1 into a unit vector. So really this thing is really nothing more than the unit vector in the direction of u1. Now, since we've just normalized everything, it's pretty obvious that our span of v1 is just going to be equal to our span of our u1, and that's going to be equal to the span of our w1. Now for our next step, we basically have this kind of picture. We've got our u2, and then we've got our v1 that's heading off in this direction. So what we want is really to just take the vector or the orthogonal component from our vector projection of u2 onto v1. And so this vector then is going to be our new vector v sub 2. And so what we then have is that our v sub 2 is going to be the difference of our u sub 2 minus that projection of u2 onto v1. Now, if it were the case that v2 happened to be 0, then it would mean that we had an expression like this. So u2 minus this scalar alpha times v1 was going to be 0, but this v1, remember what that was really just our u1. And so what we would have is a linear combination, a non-trivial linear combination of u1 and u2 that gave us 0. Well, that would contradict the fact that u1 and u2 were linearly independent. And so we can conclude that v2 is not going to be 0. And so what that lets us do then is to normalize v2, so we can take our w2 to just be the unit vector in the direction of our v sub 2. So what we've had, as we've said, is that the span of u1 then is just going to be equal to the span of v1, which was the same as the span of w1. And because we have this reversible relationship between the u2s and the v2s, that is enough to really show us that we have that the span of our u1 and u2 is going to be equal to our spans of our v1s and v2s. And since our w's are just normalizations of those v1s and v2s, that's going to be equal to our span of w1 and w2. And so if we look at the inner product of v1 with v2, then what we have is our v1 inner product with our u1 minus that projection of u1 onto v1. So V1 with V1 times V1. So now if we again use our distributive properties for our inner products, then we have a value of V1 inner product with U1 minus the inner product, so we can take that scalar multiple out. So we have U1 V1 divided by the inner product of V1 with itself times the inner product of V1 with V1. And so what happens there? We just have wonderful little algebraic relationships. Our V1s cancel out, and so we're left with our V1 inner product with U1 minus our U1 inner product with our V1, which by our symmetry relations gives us 0. So V1 and V2 are going to be orthogonal, and hence we have that our W1 and W2 are orthogonal. So now we kind of assume that up to some j that we have our vectors V1, V2, all the way up to V sub j, where we have our V sub j equal to our U sub j minus the sum, I goes from 1 up to j minus 1, of our projections of U sub j, V sub I, over the V sub I inner product with V sub I times V sub I. So we have minus the sum of these projections of U sub j onto the V sub i's, that our set V1 up to V sub j are not just linearly independent, but they are orthogonal. And furthermore, that the spans of our sets V1 up to V sub j is going to be equal to our spans of our U sub 1's up to U sub j's, and hence, since they're just normalized, our spans of W1 up to W sub j, where our W sub j is just going to be the normalized version of V sub j. So again, what do we do for our next step for defining our V sub j plus 1 equal to our U sub j plus 1 minus the sum, I goes from 1 up to j, of those projections. So we take U sub j plus 1 inner product with our V sub i's and divide that by the inner product of V sub I with itself times our V sub I. Then if our V sub j plus 1 was going to be 0, then we would have that our U sub j plus 1 was going to be equal to the sum, I goes from 1 up to j, of these projections, so U sub j plus 1, inner product with V sub I, all over my V sub I, inner product with V sub I, in the direction of my V sub i's, which makes U sub j plus 1 in the span of our set V1 up to V sub j. But then, by our assumption, that was going to be the span of our U sub 1's up to u sub j's. Well, that would mean that we would have a contradiction that our set u1 up to u sub j plus 1 was linearly independent. And so we have to conclude that our v sub j plus 1 is not going to be 0. And again, having this kind of reversible equation between the u sub j and the v sub j means that our spans of our sets v1 up to v sub j plus 1 is going to be equal to our spans of u sub 1 up to u sub j plus 1. And so if we, again, since v sub j plus 1 is not 0, we define our w sub j plus 1 as being the normalization of our v sub j plus 1, then we actually again get that this will be equal to the spans of our w sub 1 up to w sub j plus 1. And so kind of by the principle of math induction, we can do this for any of our vectors from 1 up to k, or however many vectors that we have in our set. And so our conclusion is, or at least the big punchline that we can take away, is that our Gram-Schmidt orthogonalization procedure will allow us to really take any set of vectors, u1 up to u sub k, of those vectors that are linearly independent, and we can transform those into a new set of vectors, w1 up to w sub k, that give an orthonormal basis for the span of our set of vectors u1 up to u sub k. And where we go with this, you'll just have to wait and find out.